Good morning. My name is Vladimir Kolesnikov. I'm a software engineer at Prime-Based Technologies, and together with Paul McCall, I participate in the development of PBXT storage engine. Am I heard to microphone? No, not really. Is it okay? Okay. And today I'm going to talk about PBXT performance, about the different aspects, the performance from the inside as we implement it, and performance from the outside as you see it and as you can tune it up. I will also briefly describe the architecture of the PBXT, which is needed to understand certain points of performance optimization.
You need to speak to the microphone.
Okay, like this. Hello? Okay. Yeah. So the contents of my presentation is a short introduction to PBXT, its features, and so on, how it's developed, by whom, and then I will talk shortly about the performance improvements that we've done so far. Basically, it's for your information style kind of information, so you see that it's not a magic, it's just some certain actions that lead us to achieving very good performance. And well, these improvements are still quite generic, so you don't really need to understand a lot of PBXT architecture details in order to understand the improvements in the matter of them. Then I will give a short overview of the architecture, which will be needed to for the last point of the presentation, the performance tune-up, so you will be able to understand what's going on inside and which variable influence which parameters. So about Prime-Based it's a pluggable storage engine for MySQL 5.1, and further, it's also available for Drizzle, it's available for MariaDB, and it's gonna be included, and it's already included in a number of distributions such as XM, and as far as we know, OpenQuery is also going to include PBXT when they will ship 5.1 server. It's transactional, it's ASIC compliant, it supports repeatable read level of compilation. It's fully durable. It's open source. It's a community project. One specific of this project is that this engine was specifically designed for MySQL, and it has the architecture suitable for MySQL, and the official website where you can find the latest news, downloads, documentation, and so on is www.prime.org. And sorry, it's all information. It's no more hosted by SourceForge. It's hosted by Launchpad, and just Launchpad.net PBXT, and you will get the project, and you will get the source code with the latest version, and so on. Talking more about PBXT features and design principles, it's MVCC, but unlike, for example, Falcon, all versions are stored on disk. It has log-based architecture, which means that in foreground, when transactions are committed, all writes are done only sequentially. There is no random writes in foreground in your user threads, which is very important to achieve good performance. It never updates records in place. This means that it always allocates new versions of records whenever it executes an update statement. This is not true in only one case, when you have multiple updates of the same record within the same transaction. Then it's just overwritten. Otherwise, a new version is allocated and put to the record version list. Yeah, it doesn't have undo log or other funny stuff. All uncommitted data just thrown away. It's there is no undo operation as such when for example, during recovery and similar operations. And it doesn't use table spaces. There is a file per table. We maintain actually 3 files per table. It's a handle data file where most of the records reside, the index file, and raw file, which is needed to maintain record version. And there is, of course, MySQL specific FRM file. That's for general information. The improvements since the version 1.07 RC that was released in December 2008, we focused on 2 goals, which might sound contrary, but still we were able to satisfy them all, or we are moving in that direction, I would say. It's performance and stability. We are not adding any features. We're just working on bug fixing and benchmarks, real workloads, and so on. The things that, so since the version 07 till current state, the performance greatly improved, and I will show some graphs a little bit later. But first I will briefly describe how we achieved it. First, there was we were doing a lot of sleeping on the log weighting operations, both for sharing resources and for raw logs, and that appeared to be very suboptimal. So we have to reduce the wait times to sleep for very small amounts, and also in some cases we had to replace calls to operating system sleep functions with spin logs, which appear to be very useful on multi-core machines. Another thing that greatly improved our performance was minimizing the number of mem copies. We had several cases where we had to where we did mem copy when we worked with cache, because basically we accessed the cache like this, so we read a page from cache and then to a local thread buffer and then worked with that page. And we had to change, and this is where a lot of mem copies took place. We changed that. Now we access directly the cache, which basically gave us big performance improvement. And another thing, which is also, by the way, related to reducing mem copies, is that we added so-called page index page handles. This thing that allows, for example, when the page is accessed by readers and accessed by writers at the same time, the writers do not wait for readers, they just write another copy of page, which is then replaced when the readers are done. The basically copy and write approach that we use for, that we implemented for index scans. Yet another thing related to indexes is parallel index updates. Before that, we were just locking the whole index structure when we did update. Now we lock only the pages that are updated, so it's possible to update different pages by different threads. And another thing that also helped us, basically, it helped not the inside the engine, but it helped the optimizer to choose better query plans, is improved selectivity estimation. Which we do during table call. That's basically it. And to summarize what are the results of our improvement of our changes, I have prepared a small graph that shows our performance compared to InnoDB, both InnoDB 5.1, which is shipped with the MySQL 5.1 version standard and InnoDB plugin 103. This is read-write benchmark, sysbench OLTP standard mode, 10 million rows table, and which is important, this was done on SSD drive. I remember during previous talk somebody asked about performance of InnoDB on SSD. Well, maybe here's the answer. You can see how it performs and how we can compete to it. So you can see that it was done on 8-core machine. So you can see that when the number of user threads doesn't exceed the number of cores, the performance is almost the same. But when the number of threads goes higher, we scale a bit, somewhat better. Well, you can see how much better. Basically, the work on optimization and performance optimization is still in progress, so this should be not understood as final results. We are still working on it, and you can follow our blogs to see latest results. Yes.
How many hardware threads did you say you have on here?
How many threads?
Yeah, like how many cores?
How many cores? 8.
8 cores, okay.
Yeah, it's an 8-core machine. Now I'm going to give you a short PBXT architecture overview. So, first thing that might be different, that differs the PBXT from other engines is its record structure. The record is basically split into two parts. The fixed record part, where go all fixed size fields like integers, chars, and so on, dates, and variable size data record tail, which goes into data log file. There go usually varchars, blobs, unless you use our blob streaming engine, and things like that. This second part is optional because, as you understand, it's actually up to algorithm that decides whether this extended path should be used during table creation. There is an argument, average row length. This is the standard MySQL syntax that we make use of in order to also make decision whether what should be the which fields should go into the data log file and whether it should be created at all. The row structure. This row structure basically shows the MVCC list implementation used by PBXT. Basically, we have a dedicated file for that. It's a row index file which contains simply the pointers to the records in another file, in the handle data file. And in handle data file, every record also contains a pointer to a previous version of the same record, if there is any. So you can see that it's organized in a list. So, for example, when you have a table scan, first the engine reads data from record index, row index file, and then it navigates to the proper version of the record in the handle data file. Background threads. It's quite important to understand the operation of background threads in relation to performance tune-up, because background threads do a lot of work that in other engines is done in foreground. So there are four main background threads. I would say there are other which write and otherwise manage PBXT data. The writer thread basically moves the data from the log. If you remember, I said that the data in foreground is written only to logs, only sequentially, but then it needs to be moved to the handle data file. And what this writer thread does is moves the data from the transaction log to the data record to the handle data file. or simply record file, and to the index file. It updates these two files. And also this, yeah, okay, we'll talk about this later. The sweeper thread. Sweeper thread maintains record versions as transactions go by. For example, when transaction finishes, it becomes ready for sweeping after a certain amount of point, after a certain amount of time. And it's the sweepers work to detect which transactions are ready to be cleaned and which record versions are already outdated and could be removed and reused further. So it marks, basically, sweeper's work is to mark records as clean, either clean used or clean free, and write this all information back to the kernel data file. Compactor thread works with the data log. This is the file that contains record tails, if there are any. And basically, its operation is very simple. What it does is when the amount of, as I said on previous slide, the records that become free on the handle data file, they are marked as free and then reused for other rows or other records. So they are used. This is not true for data log files. There, the record. This is so because in the data log file, the tails are variable size, so it's not easy to make efficient reusage of this variable size record. So we use different approach here. Basically, we track how many data in the dlog file is garbage, how many tails are not used anymore, and if it exceeds some threshold, which is controllable by PBXT variable, and this is by default 50%, the compactor thread just creates a new file and copies all non-garbage, all used record tails to this new file. The old file is then either reused or simply deleted, depending on, again, on the policy, which is controlled by a variable. Checkpointer. Checkpointer makes sure that data till certain point in transaction log is synchronized to handle data files and index files. As I said, writer writes the data to handle an index file, but it doesn't call fsync, and data might be cached somewhere in file system cache or in operating system page cache. And this checkpointer that makes sure that the data is already written is already on physical media, and then it writes small so-called checkpoint restart file. And if a crash happens, the recovery thread, which very similar to writer, simply starts to recover not from the beginning of the X log, but from the certain checkpoint as marked by the checkpointer thread. So this just helps to make the recovery much faster. And yeah, as I said, the recovery is all pretty much similar to the writer thread. It just reads the transaction log and applies the information to index and handle data file. There is also something that is not shown here. There is an index log file which is needed, which is written when we modify index file structure, not the records themselves, not the record index pages themselves, but for example, when we add a new page or delete a page from index, we modify a structure, and to keep it consistent, we maintain an index log file which are also processed by this recovery thread. So that was just a quick overview of the PBXT, how PBXT manages the data, and now I will give an overview of how you can monitor and tune up PBXT performance. So basically, there is a PBXT statistics plugin which is installed together with the PBXT engine. And it's an information schema plugin which basically creates a table in information schema. This table is virtual, dynamic, it's not stored on disk, and it gives the information about various performance characteristics of PBXT. There are 6 groups of counters: transactions, record files and cache, index files and cache, transaction log, data log, and background threads. That's the areas of the engine operation which are covered by the counter. Transactions. Commit count, all pretty obvious. A rollback count, also pretty obvious, but watch it if it's too large. If the amount of rollbacks large, this might mean you have a large number of deadlocks that can be resolved, and therefore the transactions get rolled back. Number of read and write statements is also available. Selector count, insert, update, delete. Wait for transaction count. Whenever a transaction has to wait for another transaction, for example, if the transaction updates a row, or if the ground thread has to wait for transaction. An internal PBXT function that gets called, and this function just increments this counter, so you have an idea of how many convention there is inside your inside the engine. The following group of counters is related to records and index. Number of bytes read. Read means read from the outside of the engine. This is not necessarily direct disk I/O. This could be file system record cache. File system cache or operating system page cache, because operating system cache or file system cache, because PBXT actively makes use of both. The same bytes written is also number of bytes written to this to the outside of the engine, to the cache or to the disk. Number of file flushes is basically the number of fsyncs and msyncs issued by the engine. This would be either commits or checkpointer, calls to msync of checkpointer. And flush time is the number of milliseconds. Yeah.
It doesn't break it down into the file system or what. That's just the total.
Yeah, just summary. And the last counter is the duration of the operation in milliseconds. So you can have an idea of how much time it takes. Yes, the following counters are about record cache and index cache. There are 2 separate caches, so there are 2 groups of counters. They're just similar, so I put them to the same group. Cache hits and cache misses, well, quite obvious. Cache freeze happen when the cache gets overflown and needs to be flushed. This happens because basically PBXT record and record cache is dirty record cache. We use file mapping to read the data, but when the data is written to the engine, when during updating insert statement delete, the data goes first. It goes to the log, but it also goes to the cache. And whenever this cache gets full, there is a special process that is run to free up some cache to the disk, and this counter shows how many cache-free calls was made. Cache usage is given in percents, and scan count, basically the number of times RD next. Well, I'm not sure. RD init was called. Yeah, RD init. That's number of times that table was scanned. This happened not only during select, but also during update, delete, and guess outer table also introduced as well. There are some counters that are specific to indexes. I mentioned already index log that is used to maintain a consistent index structure, and you can see how intensively the data is written to this I-log. Usually you shouldn't see much I/O here because the log is very small and it only reflects the changes in the index structure. Transaction log. Transaction log bytes in. Transaction log is read by writer, sweeper, and recovery, and this amount is incremented by this count is incremented by this thread. Bytes out. This amount. What is important to remember about it is that it's written in foreground, so you can have idea of how intensive I/O you have in foreground per line thread. Log file syncs is again just a number of times a sync was called on the xlog file. Sync time is how much time did it take, and cache hits just well. Yeah, that's okay. I will talk about cache misses. Well, basically, cache hits for writer it should be 100% because a writer thread always reads from cache, and the only background thread that uses transaction log and can cause cache misses is sweeper. Okay, it's written here on this slide. The presence of the cache misses produced by sweeper means that the sweeper is far behind. I will talk about this later, and we'll show a slide where I explain in more details why this happens and what picture do you see in that case. And xlog cache usage is again cache usage in percent. The only thing is that sooner or later it gets full because it's basically a first in first out buffer, so it gets filled. So you should not pay much attention to 100% or near 100% usage of xlog cache. What you should pay attention to is the cache misses value. Data log is the data log is the log where you remember the record tails are kept. Basically, the statistic counters are the same. Again, the syncs are performed in foreground. Otherwise, it's quite trivial. Bytes to checkpoint is a number of data that needs to be flushed out and synchronized to this byte checkpointer. Usually, it's an amount in range from 0 to PBXT checkpoint frequency, variable value. I say usually because when checkpointer starts to synchronize data, some more data can be added, and we can see that the amount that these values exceeds the value of the variable, but that should be only a temporary situation. And log bytes to write is the amount of data to be processed by writer. That's the amount of data that has been written to the transaction log, but has not yet been written to the data handle file and to the index file. Sweeper. Basically, sweeper bytes to sweep again the amount of data to be read from the transaction log by sweeper in order to understand which transactions should be, which record, should be marked as free, and the number of data, amount of records to be marked as free. Well, it's number of bytes, but you can understand how many records there are. sweeper waiting exact is an amount of times the sweeper was waiting on for certain transaction. Again, if you have high contention, this amount will be high. Otherwise, you won't see much too high value in this count. And dirty transaction count is basically, well, basically that's the main counter for which makes sense for a sweeper. That's the number of transactions that a sweeper has to go through and to sweep to clean them up. That's the counters themselves. Now I will give you an idea of how you can monitor them and which tools we use internally and which tools you can use yourself to perform monitoring and tune up. Basically, we have one tool. It's XTstat. Of course, you can just read the data directly from SQL table, but this is not very convenient. What is more convenient is to use tool like IOstat or VMstat, and XTstat is such kind of tool. Just brings you snapshot of the counters after certain periods of time, after a second, so on. That's, you are not intended to actually see any numbers there. It's just a review of the output. First, it simply prints the values of PBXT variables, and then it starts to periodically output the values of counters until you press consoles. Now I would like to describe some typical cases that happen during the engine operations, which can give some trouble and cause some performance degradation. So you can see, you can observe them with the XTstat tool, and you can, well, take the proper action instead of simply, for example, increasing the cache size and so on. One of the major troubles is long-running transactions. For example, if you say begin and then do a select and do nothing, the engine needs to keep all the database at the state when this transaction started, because otherwise, well, we don't know what other data transaction will want to read more, and that's why the sweeper can proceed and clean the records after the records that are not used but still visible by these transactions that got started. So the vertical scale, both in number of dirty transactions and in percent. The full scale is also 100%. So you see that at certain point the number of dirty transactions start to grow, which corresponds to the point when the long-run transaction was started. And you see that record usage also started to grow. This is because all dirty records also have to be kept in record cache. But adding, you can't solve this problem by simply increasing the record cache, because sooner or later it just will get full, and that's it. What you need to do, well, basically it's partially a problem on the application side. You need to prevent such long transactions, and the XTstat tool just gives you the way to monitor and see whether there are any. And you can see that after the transaction has ended, the record cache usage, basically this point, record cache usage has increased. Why this happened? This happened because the sweeper got far behind the current state of the transaction log buffer, and it had to read some records from disk, and in order to process transactions and mark records as free or used, and it reads them into cache, which increases the cache usage. But as you can see, after after the sweeper finishes its operation, the record cache usage doesn't drop anymore. That's it. On the other hand, the situation when you really have a small index or record cache is very different because, as you can see, it's the same by the way scale as on previous slide. So you can compare the record usage is permanently high, and we have a special process that gets run every time the record is overflown, which frees up some cache. And the major difference is, of course, that the number of dirty transactions keeps low despite the fact that record cache is very small. Another thing that also greatly affects the performance of the engine might affect is checkpoint intervals. Checkpoint, as I said, the checkpointer is a thread that synchronizes the data from transaction log to record file and index file. The threshold, as I said, is controllable, and I try to compare the effect of frequent versus infrequent checkpointing on the situation where you have large cache and large record cache and small record cache. This slide shows the situation with large record cache. So the major slowdown that you get is the slowdown caused by extras fsync and the msync faults. That's the killer of the performance. As you can see on the pages, the record cache is large. You don't want to run the checkpointer very frequently unless you have other reasons for this, because this causes the major slowdown. The crossbar that's just the same measurement made after different periods of time, after 100 seconds, 200 seconds, and so on. So you can see that for 1 megabyte checkpoint threshold, you have a very high number of fsyncs, and on this amount of fsyncs, well, it's contributed by both. This number is contributed by both checkpointer and fsync caused by commits. So you can see that, for example, at 100 megabyte, the amount of fsyncs only high when there is a high number of commit operations. That's inevitable. But the situation is very different when you have very small cache. In this, well, small cache, the different names of this situation is this bound workload. You either, sooner or later, depending on your data size, you might end up in this situation. So it doesn't actually mean that you can simply solve this situation with, by increasing the record cache. So there might be other ways. In this case, it is important to see that frequent checkpointing helps to free up some space in the record cache before it gets full, and this increases the overall performance. There are other issues which you can just move through. I will not. What I want to show is I run some tests which shows the performance of the InnoDB index scan versus other kinds of access. You can see that basically the short idea is that index scan on in-memory case on InnoDB is very fast and much faster than on other engines. You can see it on this slide. Here. And basically that's it. Thank you for listening.